You're welcome. As we wait for others, let me sketch the experiment. Determination of latent heat of vaporization using the electrical method. Jennifer, you're welcome. As we wait for others, let me sketch the experiment for determining latent heat of vaporization. That is the voltmeter, this is the ammeter. This is our heater. I've sent a better diagram on the group. No, this should be hot water in. Here we have hot water out. This is the condensed vapor. So this is the heater. This is where vapor is passing. It also passes here through these terminals. As it comes here, it's going to be condensed by this water that is running through this cooling system. This is a jacket. This is your vapor. This is water we are boiling. As you boil this water, it produces steam. So the steam it produces is the one that passes through these openings, then runs down this way to come and meet this junction. But remember, this system has a circuit which consists of a switch K. It has a battery, it has a rheostat which adjusts the voltage and the current flowing. So to begin with, switch K is closed. I've sent you the write-up plus the better illustration. So to begin with, switch K is closed. When you close switch K, what is going to happen? You're going to produce heat on the heater. So the heater will start boiling the water. At boiling point, you know, at boiling point is this point where we have the water starting to coexist in thermodynamic equilibrium with its own vapor and its own what? Liquid. At boiling point, the vapor escapes through the holes into the surrounding jacket and then passes down the tube capital T. The tube capital T is this one. Here it is condensed by cold water flowing through the condenser. This is the condenser. The condensed water is then collected, or condensed vapor is collected in a beaker, in a measured time T, and weighed. The mass M1 collected per second is measured or determined. And that mass M1 is the mass for the vapor at a steady state. The ammeter and the voltmeter readings, this is mass of vapor. The ammeter and voltmeter readings are also noted, current, the ammeter. Voltage, the voltmeter. Described by V1 and I1 are recorded. Then the electrical power supplied is equal to the amount of heat energy, because what happens is the heat energy supplied by the heater is all converted into heat, which burns the liquid, which liquid also converts the heat and makes the water convert to vapor. So is equal to the heat, which heat is latent heat. That's some heat loss to the surrounding. So we shall have I1, V1 is equal to M1 LV plus heat loss to the surrounding. So small h is heat loss to the surrounding. Now, this experiment is repeated again by varying the voltage and the current using the rheostat. So the rheostat is adjusted to obtain different set of values so that we can eliminate or minimize the heat loss to the surrounding. At a steady state, the ammeter and the voltmeter readings are also noted, where we have I2 new ammeter reading, V2 new voltmeter reading. Then a new mass is going to be collected from the vapor, mass of condensed vapor. Per second. Now, the reason why this was just power, it's because this mass ideally, M1 is technically having, for example, M over T. It is mass per time, mass of vapor per second. So if it's mass per time, if you cross multiply this time and remove the time from here to come this way, then it will reduce into energy. Okay? So electrical power supplied is equal to the heat, which is latent heat, plus heat loss to the surrounding. I missed this. So even here we shall have then I2 V2 shall be M2 LV plus H to give us equation 2. When you already attained equation 1. So this is the set of equation which comes as a result of that adjustment of the rheostat R to give us a new reading for current and a new reading for voltage until we attain a steady state. So at steady state, the power supplied is equal to the power absorbed by the water in a given time, which is the rate of mass flow. So giving us, we can subtract I2 minus I1, shall get I2 V2 minus I1 V1 is equal to M2 minus M1 times LV. With this, because the H will cancel, with this latent heat of vaporization can be got from I2 V2 minus I1 V1 divided by M2 minus M1. So we can get this value of latent heat of vaporization using an experiment which is called the electrical method. And like I've said, there's a better write-up you'll find on the group which can make you be in position to summarize your notes. I have also some other notes I'll send which are handwritten, and see if you can pick out something which can be useful. So let's take a look at an example. A liquid of a specific heat capacity (2.8 times 10 to the power and the specific heat capacity Specific latent of vaporization is 9.00 times 10 power 5 joules per kilogram per Kelvin is contained in a flux of heat capacity (800 joules per kilogram), per Kelvin, at a temperature of 32 degrees Celsius. An electrical heater rated 1 kilowatt is immersed in 2.5 kgs of the liquid, and the boiling point is 80 degrees Celsius. This number was now something is missing. After 2.5 kgs of the liquid and switched on for 12 minutes. Calculate amount of the liquid that boils off, given that boiling point of the liquid is 80 degrees Celsius. This was a UNEB number of 2014, number 7D. Now, in this regard, they are telling you a liquid of specific heat capacity that and specific latent heat of vaporization that is contained in a flask of heat capacity, that one. At a temperature of 32 degrees Celsius. An electrical heater is rated 1 kilowatt, is immersed in 2.5 kgs of the liquid and switched on for 12 minutes. Calculate the amount of the liquid that boils off, given that the boiling point of the liquid is 80 degrees Celsius. Now, to start with, in actual sense, they are looking for mass of the steam that is coming off. So I can assume the power, which is IV, is 1 kilowatt, which is 1000 watts. The time is 12 minutes, which is 12 times 60, give me 360 seconds. It's always good to identify what is given in the question. Latent heat of vaporization, 9.00 times 10 to the power 5 joules per Kelvin Then specific heat capacity of the liquid is 2.8 times 10 power 3 joules per kilograms per Kelvin. This is your capital C. Furthermore, they also give us the specific heat capacity. This is for the liquid. Specific heat capacity of the flask was given as 800 joules per Kelvin. But they never gave us the mass of the flask, did they? Oh, they gave us the heat capacity. Oh, heat capacity, remember, has what? Mass times specific heat capacity of the flask. So the whole of this is your heat what? Heat capacity. That is where the trick was in this number. So, with all that, the initial temperature θ1 was 32. Then the boiling point, the final temperature we reach is the boiling point, which is 80. So heat lost by the heater is equal to heat gained by the liquid plus heat that converts liquid to vapor. So this would be IVT is equal to mass of the... Now, when you are... This is gained by the liquid plus the flask. So it will be mass of the liquid, specific capacity of the liquid, plus mass of the flask, specific capacity of the flask, times the temperature change, plus mass of the liquid that has condensed vapor, times latent heat of vaporization. Now we are looking for MV. We don't know MV. But we knew mass of the liquid was 2.5 kgs. So can we do substitution? Power is 1000 times 3600 times 360 is equal to mass of the liquid is 2.5. Specific capacity of the liquid is 2.8 times 10 power 3 plus heat capacity, which is 800 close brackets times temperature change, which is 80 minus 32 plus heat due to conversion of the liquid to vapor, which is mass of the converted vapor times latent heat, which is 900.
Excuse me, sir.
Yes, please.
Here, the heat lost by the heat is 1000 times 720.
Why? Oh, you're right. My bad. I made a mistake up here.
Yes,
This
sir.
time it is 700 what?
20.
True, thank you. So this is 700. I can't go to the next page. I don't know why. Can't see it. Let me wrap this part. So we shall get is equal to 2.5 times 2.8 exponent 3. What do you get? Calculators, can you multiply this? This first part, what do you get?
$7,000.
7,000 plus 800. 80 minus 32, you get 48, plus 9 times 10 power 5 MV. So we can make MV the subject by saying 720,000 minus 7,800 times 48. What do you get? Compute this.
Yeah. Yeah.
What do we get? 7,800 times 48.
Oh. Three thousand seven
Hmm?
374,000
Hmm.
400.
Oh, 720 minus the answer.
$345,600.
Divide.
Teacher, the answer is
Mm-hmm.
0.384.
Correct. Which is ideally 384 grams. And that is the answer. So you can have that down. So that marks the end of calorimetry. And I remember I said when you finish calorimetry, there are some graphs I want to discuss. Then I will look at some examples here. Okay, hope you're done. Now, I wanted to mention some things on these graphs to remind you how latent heat and heat capacity can be predicted, especially if they set a number, which, for example, can require converting from a solid to liquid, then to gas. For example, they can give you for example, if it's water, then you can have what we call dry ice. At this point here, you have dry ice at negative theta degrees. Then you raise the temperature of dry ice using heat capacity, which is MC change in temperature, until a point B. At point B, ice starts melting. So this is ice only, or which is solid only. Then ice starts melting up to point C. And here we shall use latent heat of fusion. This is ice plus water. At point C, all the ice has turned into water. So the temperature of ice, melted ice, starts rising. Rises until it warms up to 100 degrees Celsius, where it starts boiling from at point D. But before it boils, here it is only water. So there is a change in temperature from 0 up to 100. So here you use MC change in temperature. When it reaches vapor, it vaporizes, and then it will have to use mass times latent heat of vaporization until all the water, at this instant, we have both water plus vapor. Until you reach point E, when all the water has turned into vapor, then the vapor can be raised, its temperature can be raised to another temperature beyond 100 degrees Celsius. And the reverse is true. The graph can come when starting from up there. This can be how much heat is required to convert ice at negative theta to maybe vapor at 100 or beyond 100. If it is vapor only, it will stop at E. So you have to sum up the heat as MC theta plus MLF plus MC theta. Again, this is MC theta 2, MC theta 1, plus MLV. All this will be the total heat energy required to convert ice at negative theta degrees to steam at 100 degrees Celsius. They can as well tell you to condense steam. They can tell you to condense steam back to ice. Maybe steam was at 100 degrees Celsius. So steam at 100 has both. Here it has steam alone. When it starts condensing, it shall use latent heat of vaporization, and we shall have both water at this instant plus steam. Until we reach a point when all the vapor has condensed to water, but this water at this point, this is A, this is B. At this point B, the water is at 100 degrees Celsius. Then the water will fall in temperature from 100 degrees Celsius to 0 degrees Celsius. At this instant, water will start changing. We shall use specific latent heat and temperature change. Here we shall have water only. So whenever you have heat capacity, you can have two states. You can have only one state. But if you have two states, we can have what? Latent heat. Remember, latent heat of vaporization is greater than latent heat of fusion. The explanation we gave was the other one uses one, energy to separate the bonds of the molecules, and two, to give the bonds, the molecules kinetic energy to free themselves from the surrounding attractions. while the other only just breaks the intermolecular forces of attraction. So the other needs more energy. So when all the water is condensed to 0, then water here starts freezing. It starts freezing at point C. When it starts freezing, water is mixed with ice. And they are using latent heat of fission. So all the water until it reaches point D. Point D, all the water is converted into ice. And after all of it has converted into ice, then ice starts drying up until it reaches negative theta degrees again. So they can give you a question, for example, calculate the amount of heat energy required. Example, how much heat energy is required to convert 2 kilograms of ice at negative 10 degrees Celsius to steam at 100 degrees Celsius. This is what I was talking about. So the theta can be negative 10. So you move the dry ice from negative 10 to 0. So the heat energy will be mass of the ice, specific heat capacity of ice, temperature change for ice, plus mass of ice melting times latent heat of fission, plus mass of melted ice times specific capacity of melted ice times the temperature change for melted ice, plus after that we reach 100, mass of melted ice times latent heat of vaporization, and then we shall stop there. But of course, melted ice, mass of ice is the same as mass of melted ice, because the question is assuming that all the 2 kilograms of ice have been converted to water, at the same time all those 2 kilograms of ice have been converted to vapor. So the mass is the same throughout. While specific heat capacity of ice is 2100, specific heat capacity of water is the same as specific heat capacity of melted ice, which is 4200. So we shall have heat energy is equal to 2 times 2100 times 10. This first 10 comes from 0 minus negative 10, plus 2 times 2.334000, latent heat of fission of water, plus 2 times 4200 times 90. How does the 90 come about? The new temperature, which is 100, minus 0 gives you 90. Then lastly, plus mass of the ice, which is 2, times latent heat of vaporization, which is 2.26 exponent 6. So can you compute this and give me the answer? This question I think was in Abbott. I got it from my head, but I know it's in Abbott. And if you get challenges of understanding some concepts in A-level physics, please go back and read Abbott. It can help you in understanding. So compute that.
Teacher,
Yes, please.
I thought 100.
Hmm?
100 by 0. You've subtracted.
This one, eh?
Yes.
Yeah. Nabizunza. Nabizunza nsomesa. Jali nabizunza nsomesa. So compute that, what do we get? I'm sending more numbers now. But you're going to try for me out question. Immediately after that, you're going to try out question number 6. You try out question number 7. Before we close, try out question number 7. I'm going to find you with. Let me first briefly go and make a prayer here as you try it out. I hope you're done. We have some answers. It's 4:30 and it was meant to be 1 hour, so I have the next class in the next 15 minutes. So I have to prepare for it. I want to look at your solutions, number 7 and number 8. Share for me those solutions in the group so that I can take a look at them. Unless if someone has a question. Very. Carmen? Guys, try those numbers I've sent. If you get a challenge, you let me know. Now, I told you when we finish calorimetry, we are going to go back to paper, to either mechanics or we go to modern physics. I think we should go to mechanics back and we see how best we can have it sorted. But I want you to, within this time, up to Monday, at least to share with me some of the workings of those numbers. And in case of any challenge, you let me know so that I can take you through.